Okay, so today we have Ahmed with us. He's really not that bad, guys, you could say. Anyways, so Ansh's friends from 40A. Anyways, Ahmed is a grad student at Berkeley in the CS program. He turned down Harvard for Berkeley, so we'll see in a year if that was a good choice or not. Yeah, so he's here to give a talk about neural networks and how he thinks about neural networks and why they're so much fun, because with LLMs and stuff, this stuff is really important, and this will help you kind of get a little bit of insight into next talk that I'm going to give, and it will also help you to kind of get some information from Ansh's demo that he's going to show with reinforcement learning. So, yep, should be an hour or so. Yeah. Not too bad.
Not that long. We'll not take the whole time.
Okay. You will.
Not the whole time. Okay. Let me split this. Okay. Hey everyone. As Kyle said, I'm Ahmed. Just a little bit about me. I graduated last quarter from HDSI, and I'm going to Berkeley for EECS. And I like playing ping pong and tennis, and actually like learning tennis from Kyle. But one thing, if you know Kyle well, you'll know that he loves Regent's Pizzeria, and I hate Regent's Pizzeria, and Regent's Pizzeria is like one of the worst pizzas that you will ever have in San Diego, so please do not go to Regent's Pizzeria. See, I told you, like less than 25%. That's significant. But yeah, so quick overview. Like today, we'll be talking about like deep learning essentially, and this is a bunch of stuff that we will supposedly, like after we're done, hopefully everyone will be able to like answer or have like a quick overview and a general idea of what everything the things that can answer these questions. So I don't know if you guys like heard about deep learning or not. I mean, I'm assuming like people are here either like taking COGS 9 for GE, or they are like first years data science or cognitive science students, and like you still didn't get into upper division for machine learning. So it's good to have like an overview of like what deep learning is. So one of the things that we'll have to understand when we talk about deep learning is that when people are like trying to come up with this algorithm, they were thinking like we're trying to make something that is similar to a human. But then like what is like if you think about it, like let's see who here like thinks of like walking. When we walk, what do we actually think about? Like it's just something that happens subconscious, but if you actually think about it, you will know that there are like multiple steps that go through like this action of just like stepping in front. Things that like you're thinking, oh, you're telling your brain, I want to move my leg, and then your brain sends signals to your foot, and their foot like starts taking action and so on. So there are a bunch of things actually, not only walking, like reacting. Like if I throw some object to someone, they will try to catch it, just like fearing it will fall, although like maybe it's something not necessary, it can just fall. So reaction is also like a bunch of steps that happens. You take in an image, like an eye, that you see something coming towards you, and then you react to this. So there's a bunch of steps that goes through it. And I don't know like how many of you guys here like thought about how Face ID works. Like if your phone, like anyone here like has an iPhone or like any phone that has a Face ID? Anyone thought how does it work? Anyone? Yeah. How does it like? What did you think about like when you were essentially like what are your thoughts about it? How does it work essentially? Yeah. Okay. So how do you think like we reached to this technology? Like our technology, like 15 years ago, there was no Face ID. Nobody knew about what Face ID is. And if you actually see like learning, like our machine learning and deep learning and AI and all these like things, of course, like the biggest umbrella is like AI, and we'll talk about it later, like how the layers work. But essentially, this is the evolution of like how we were able to generate images, how our models are able to like get better and better about like certain tasks, like just generating images. So in 2014, that was like the best we could do. Like some like random guy, I mean, of course fake, and it's like black and white without like clear like characteristics for the face. And then you start getting better and better, and then like now it's like a normal human being that you can't even know whether they are real or not. So it actually like, it will be like very like triggering to understand like how we came as a human beings from this 2014 image generation to 2019. How did we make our models do this? And it actually goes through only a bunch of steps that we just started looking at the details of how we as humans operate. We started looking at like comparing us to computers, which actually raised like the evolution of like neural networks and like how it connects to our human brain. So essentially, like if you know how neurons work and like in brains, like I'm assuming like it's a cognitive science class, so supposedly everybody knows how a neuron should look like, and it's like something like this, and then like this, and then you have like an axon, and then like terminals and whatever, and then you have like the dendrites. So essentially, like just scientists started looking at that, like how our brain functions, and it suddenly found like, oh, we have this thing like a neuron, and then these things like are like connected. Each of them are sending signals, and then step by step it reaches to a conclusion and output. So it gets in some kind of information, it processes it, and then sends it out to some other neuron that will accept it here, and then so on. And then it will be like a cyclical information of like, oh, you're sending this information, sending it to another neuron accepting it, doing some process, and then it goes on. So this was like essentially the first step of how like scientists like decided to make neural networks, where they just started creating a bunch of neurons for processing stuff, and then they started sending out this information into some other neurons until we are able to execute an action, which is essentially what we were talking about, like walking, for example. You started by thinking, you gave in an input, which is like the thought, you gave it to the brain started processing it somehow in some like layers here, and then sent some other information, which is the target action, which is like you starting to walk. So essentially, like the artificial neural networks is just like the whole network like you have here, where you have a bunch of layers, and each layer consists of a bunch of neurons or perceptrons. They're called perceptrons. And then you go from an input to an output. And this whole thing, artificial neural network, is like the neural network, and a subset of the artificial neural network is a deep learning. So we will talk about like this more into like the slides, and we'll discuss like what is like artificial intelligence, machine learning, and then deep learning. But yeah, so cognitive science is like essentially very like, if you look up what is cognition or cognitive ability or things like that, it's like the ability of like thinking and knowing of like learning, how you're learning. This mental thought is like what we want to transfer to our computer, how the computer can become more and more like us so that it's able to make our tasks, like you can see like right now, like a lot of agents and like AI agents that you can develop with just like 3 lines of code, and they can like make like crazy stuff. Like for example, like a couple of weeks ago, I was in a hackathon, and then we built that agent that just by your address, and you can talk natural language, make mistakes in your spelling or whatever, and then it will tell you exactly how much solar power you can generate from your house, and like what are the carbon footprint you're like saving and things like that, or like any information about emergency resilience, all of this information just by your address. So, and this was like only a couple of lines of code. It's not even that hard. So it's crazy what we can reach like by just trying to look at our like brains and how we operate and trying to transfer it into like our computers to make our small steps. So By the way, if anyone has any questions about anything, I will start talking about neural networks, and if you have anything that is confusing, just let me know. So let's start about talking about neural networks. Neural networks, as I just said, it's just a bunch of perceptron. A perceptron is just a node where it has a prediction, I would say, which is just without too much math, you're just giving some inputs, and then you're multiplying them by some weights, and these weights are just saying what are the inputs, how much are they important towards my output, and then they return a specific output. And then this perceptron will have this output, and will pass it through another layer, which we'll talk about, which is called an activation function, or a function, that essentially will introduce some other variability in our data, so we are able to make capture the noise and the different variance in that data all over the world, essentially. But yeah, so essentially as we saw here, when you have a neuron, a perceptron here, it will pass to another neuron, and it will pass to another neuron, and then that's the output, essentially. So we can see here by just comparing the neuron to our perceptron or neural network, you will have the perceptron, which is let's say it's the processor, which is the cell body of the neuron. It got some inputs from our data. It processed it by this mathematical function that I was talking about, and then it sent it through the axon, which will have the activation function that will say whether it will pass or not, and then it will give to the second neuron, and it moves forward. So the analogy that I gave here is essentially a bunch of light bulbs. Then once a light bulb is triggered, it may trigger the next light bulb. So if you know that they're connected, and then this activation function that I was talking about will decide that this input is actually useful, it will allow it to pass through and then continue with some other processes. So let's say your brain, I mean, this might be not a very accurate analogy, but essentially your brain, you're thinking to walk, but then, oh, you see it's a cliff, so you're gonna step out, but then your brain will just stop you. So it's the activation function just stopped you from falling, essentially. But yeah. So let's explore more about the architecture, or how does a neural network look like. So we have here the input layer, and then you have here some other layers, and then you have here layers, and then all of these will combine into an output. So essentially in machine learning, how we essentially teach a model or make a model learn, we give it a bunch of data, and then it tries to find a pattern in this data. And then in this pattern, it will identify the variance and how it correlates with the dependent variables from the independent variables. So the independent are the ones that are provided, which is the input layer, and then the dependent variable as the output that you're trying to predict. So let's say, for example, in healthcare, you want to predict by a bunch of symptoms, like your temperature or your blood pressure or whatever, and then you want to try, oh, does this guy have let's say diabetes or whatever? I mean, whatever disease we're trying to check. So our neural network will just be split into multiple layers, and these layers are just a bunch of perceptrons, vertical perceptrons. When we draw it, we'll just draw it as vertical perceptrons. And then the first layer, we would call it input layer. And you can think of the input layer as to compare it to your human body, it's your sensory ability. So let's say when I touch this bottle, now I got some information from, my brain got some information that this thing is plastic or something that I can press. I felt it. So this sensory data that you're getting in, we can essentially take it as an analogy to the input layer. This sensory, our sensory ability will just, once you get this information, you're able to process it somehow. So here in the hidden layer, and why do we call it a hidden layer? Because just simply in our computers, we do not actually see this part. We just give it the input layer, and then it will return the output layer. It will not give us the intermediate. There are ways, of course, around it that where you will be able to like check it and things like that, but that's why essentially it's called hidden layer, because you don't see the middle steps. Same as in your brain, you don't see like the synapses that happen in your brain. You don't see like these things. You just know like, oh, I'm thinking and then this action happens. So you saw the output, you saw the input, which is like, I want to step my foot here, and then you took the action. So you saw the input and the output. You did not do anything in the middle, or you did not feel or sense anything in the middle. So yeah, so these hidden layers will also have a bunch of like processes that will essentially make us like find the most patterns in our data. And one thing we'll also mention later on is talking about like the data that we're going to use, and why didn't we have like deep neural networks from the beginning, and also why is it called deep neural network? Why is it not only neural network? What is the difference between deep neural network and neural networks? And actually, like simply, like neural networks and deep neural networks is just the same thing, but deep neural network is just a neural network with more than 2 hidden layers. So if you have like 3 layers, then you are deep neural network right away. So it's like very simple and like seemingly stupid, but I mean, the more layers you add, the more complex, and it grows really, really quick how like complex your model can get. So as I said, like after explaining here like your different layers in a neural network, we have the activation function, which passes like essentially, which decides whether this neuron or this output would pass or not, or in what shape would this information pass. So essentially, an activation function is simply, we'll explore a couple of them in the demo that we're going to do together. Essentially, just one of them is called, for example, ReLU, which is like rectified, like linear something. But essentially, all what it does, it takes the max of 0 and the value that you got. So it just says if my neuron or perceptron got a negative number, I'm just gonna put it to 0. If not, I'll just keep it as is. It's kind of simple. However, like this small step introduces a lot of nonlinearity in our data. And notice that I mentioned nonlinearity multiple times, but why do we actually need this nonlinearity? So if you think in like a simple classification problem, where like, let's say you're given an image and then you're trying to classify whether this thing is like a dog or a cat. So you have here some points, and you have here some other points, and then you're trying to separate them. A linear model would just separate them that way. And you successfully separated them, and you're able to classify anything to the right of that thing. You'll just say it's a cat or a dog or whatever, and then the left will be something else. But what if we have like data, which is what we usually have, is like some data that is like this? Are you able to find a linear like line that would separate these data points? Are we able to do that? Anyone? I don't think we can. But essentially, like when we have this kind of data, we need some nonlinearity in our prediction function or in our model. Our model can always be visualized as in a classification problem, can be visualized as a decision barrier, where like you're able to say anything in that region, our model is going to predict that kind of stuff. So we want something that is like able to isolate these points. And now, this is not linear at all. In order to introduce this nonlinearity, we need this activation function, where it will just like introduce a bunch of like random stuff in order to be able to get these curves in the data. Yeah. So, yeah, so the analogy that I was talking about is like, is this important enough to pass through or not? So is it useful or is it not useful? And Going to the next step is going to be backpropagation. And backpropagation is actually math heavy, but we will not be talking about the math too much for it. We're just going to keep it very high level where we'll say like backpropagation is just a way where the model is able to learn from its mistakes. So a kid, for example, learning how to walk, they will just like try to stand up and then start walking and then they fall. And then they start how to walk and fall until they are able to like walk normally. Same thing, our model will learn from its mistakes. It will have very bad accuracy. It will be like 50-50, just a random guess. And then it tries to learn step by step. And how does it learn? It just like gets a treat, or it like finds that, oh, I scored higher, or like I did not do that much of a loss. And Kyle mentioned like once just slightly like the loss functions. And loss functions are essentially a way for the model to like have a benchmark of how well am I performing so far? Am I doing well or am I not doing well? So learning from the mistake, iterative process, you go back, it passes through, gives an output, it checks how well did it perform. And if it didn't perform well, it will go back and learn again by adjusting each of the values that it assigned to the perceptrons, which is the W's. W's are weights. Weights are just like, it gives importance to each feature. So it will just reassign these weights so it's able to like say which feature is actually more important until it actually finds the most important features in order to get the best accuracy, essentially. So next, we'll just play around with neural networks here. Let me do this here. Yeah. So this is, it's public available. This is, I forgot, I think it's TensorFlow. It's given by TensorFlow Playground or something like that. Essentially, it's just a playground where you're able to see how neural networks converge, and you can adjust the layers, you can adjust a bunch of other parameters, but like we didn't talk about a lot of the parameters like learning rate and things like that. These are related to the backpropagation, and this is related to the loss functions. But these like are more advanced stuff where you can, if you want to learn more about, of course, if you're not data science or COGS major, you're probably gonna learn, if you want to learn more about it, you should take like DC 140B or DC 140A, CC 151A, and CC 150B. So these are the 4 courses I know of that talk about these. But yeah, so anyone wants to play around with this? What can we do? And just a quick thing, which is the noise thing. The noise means how messy and variant the data is. And let's just do this here. Cool. So what do you think of this data? Is it easily like separable? Are we able to separate this kind of data easily? What do you guys think? Will the neural network be able to achieve good accuracy for this? Well, it's actually going to be kind of hard, and that's because it's too noisy, and it will get a high accuracy, but it will be misclassifying a lot of them. But if we get a less noisy data, which will tell you, and why does noise matter, and why did I mention noise? It's because of the quality of the data. So now if we have this less noise, now look at this. It almost perfectly predicts all of the data correctly. And it got like the circular shape, and it's trying to maximize how it separates completely the blue from the orange. And if you see, it's still like the epochs or like epochs, however you want to say it. It's iterations of learning. So now it did like 1,500 iterations of learning, and that's why you see it's actually getting better and smoother. So you will see like how it's playing, and you can adjust how many perceptrons you want to add, which is the input layers, how many hidden layers you want to add, and this will actually make it even better and faster. You can way faster reach like the optimal solution essentially. So in less number of iterations, you were able to reach the best solution. Okay, so far, anyone have any question about any of what I've said so far? Neural networks, deep learning. Fancy words, but it's actually pretty simple. And if we'll talk about, if we were going to talk about the math, it's actually like just deep hidden inside. It's actually a bunch of linear regressions that are combined together to make like this fancy algorithm. So yeah. Any questions? Nope. Okay, cool. So far we have done, let me just, how do we do this? Cool. Yeah, sorry about that. So yeah, so far, as we said, deep learning, just a neural network with more than two hidden layers. And the parts that create a neural network is a layer, activation function, and backpropagation. This is how our algorithm works. And you can essentially compare it to a neuron, where a neuron is just, you accept information, you process some information, you send out an output. 3 simple steps, and you're able to get like some fancy outputs. So what can we do with deep learning? And I don't know, why is it not pairing anymore? Okay, cool. Yeah. So here we're going to talk about like the applications of deep learning. And I was actually looking at this video at MIT, and it's like, it was essentially like the professor was trying to, like, he's been giving that same lecture for 8 years. And it was crazy how the evolution works of how he started and how he's doing it right now, where at the beginning, he was just like doing some simple, stupid models that costs like hell a lot of money. And right now, he was able, in the last lecture, which is like in January 6th of 2025, he just made a lecture of like live training a model on his voice to mimic his voice and teach the lecture and talk about it that he is giving right now. So right in front of the class, he has been recording himself, and after like capturing his voice, he is able now to give the lecture through just AI without even talking, or by just asking questions, and the AI is like giving the whole thing. So it's actually pretty cool, like the extent of like how he went from like not being able to generate an image or like some text into actually making an AI just giving the full lecture. And he mentioned like 3 years ago, they were able to, or actually 5 years ago, it's 2025 now. So it was in 2020, they were able to generate like a 2-minute video where Barack Obama were like, just like giving a welcome sentence for the students in that class. And that video he said like it costs $15,000 and 3 hours of work in order to get just a 2-minute video. Right now, you're able, just by asking ChatGPT, generate a full like series or a show in like a couple of minutes, and it's like insane. But yeah, so essentially, deep learning helps us understand more information and allows us to capture more and more variability in our data and gets all the information that we as human beings are able to perceive. Right now, I'm able to see you guys. I'm like getting a lot of information right now. Like if we get a camera and takes this, it will be like probably like hundreds of gigabytes of information. And you're just processing it live right now. Same thing that we're trying to improve is like trying to capture this information and be able to learn from this pattern and make it like in natural language where it mimics exactly how a human being works. Yeah, so just to briefly mention the diagram here, where like you talk about artificial intelligence versus machine learning versus deep learning. So artificial intelligence is essentially anything that makes a computer like performs a specific task. Anything, a human task, like a task that normally a human would do, then this task, or like this thing that the computer is doing is called artificial intelligence, where it's able to do something a human, like that requires intellect. We call it artificial intelligence. However, like when we go deeper, a specific subset of like artificial intelligence is machine learning. And machine learning is essentially just a way of like learning from patterns in data. So you're given a bunch of numbers, you're trying to learn this pattern. And once you're able to get this pattern, they are able to infer and give some predictions about like hidden data. Oh, I'm able to tell you what's going to happen, or I'm able to tell you what is the predicted value for this thing, or actually this is what happened if this is the data that you're giving to me. So once you go deeper into this, a specific subset of like machine learning is where your model, or like the way you're learning the pattern, involves a neural network. And when it involves a neural network with 2 or more hidden layers, it's called deep neural network or deep learning. So it's getting deeper and deeper into the features of the data in order to get its output. The more layers you add, the more complex you get, the more patterns and the more like variance you're able to capture by your model. However, there's a lot of drawbacks and disadvantages that we will talk about, and about like why don't we just like do an infinite number of layers and infinite number of perceptrons. Yeah. So here. So these are a couple of real-world examples of like things that we actually use deep learning in, like voice assistants, or like Siri, for example, probably uses deep learning. Healthcare assistants. For instance, like my capstone project was actually with Kyle. It was like about healthcare, and we're trying to essentially predict whether a person has sepsis, which is like a disease where like your immune system overreacts to your infection. So we used something called ResNet, which is a deep neural network. We will also talk about like it actually encompasses both like being a deep neural net, and it uses something called transferred learning, which we'll talk about at the end of the lecture, where you are just not reinventing the wheel. So healthcare diagnostics is one of the most like essentially like hot topics right now, where like people are actually trying to use AI in order to give you the best like diagnosis, because AI is able to see things that humans even can't see, because it can essentially perform on the level of a pixel. Pixel is just something like that a human can't even see. Like you see millions of pixels, but like just a specific one, the AI would be able to like identify it and say, oh, maybe that thing is actually causing a problem. Yeah, and then like there's a lot of other research like related to any kind of industry that you're thinking about, like from like agriculture to construction and to healthcare. Any industry, you will find deep learning actually useful in that industry. Yeah, so any questions so far? Am I moving too fast, too slow? Everything is going well? Cool. So I think right now, like we are able to identify what is deep learning, or like define what deep learning is, define the components of a neural network, and things that we could possibly achieve with a deep neural net. And the fourth thing is like the difference between deep learning and other regular models. And actually I forgot to mention that, but essentially the difference is, I did not make it clear, however, like the difference between deep neural net and like other regular models like linear regression, or like some other thing like SVM, for example, which is like something that will be like this. There's a lot of models that are out there, but the deep learning is like a way of like, it gives a lot of flexibility to your model, that it captures the most complex and the most nonlinear patterns in your data, while other models are not usually as flexible. Like linear regression, just a straight line. You can do, or like you can get it like into a more flexible by adding more features, or like there's a lot of details that goes through it, but it does not get as complex as a neural network. Okay. So next, of course, like with this much power, we can't ignore like ethical considerations that we need to consider while using such a thing, because there's a lot of things that we can actually like fall into when using deep learning. Some of which privacy stuff, it can be like crazy. Like ChatGPT, imagine you can like ask ChatGPT about someone's personal life because it's able to capture all of the data on that social media or everything about a person. That's gonna be insane. Like anyone can know anything about any person. That would be too much. Like for example, there's like the MIT students where they're able to program this model where using like the meta like eyeglasses, I forgot what it's called. But essentially just using eyeglasses, they're just walking around and it's just taking a photo of every single person they are like seeing on the street, and they're getting all the history of that person that is available on the internet. Just imagine how crazy that is. Like just a random stranger knows everything about you in front of you, just like by a few seconds of staring at you. So there's a lot of ethical consideration that go through it. How about like, for example, things that can happen related to like, I don't know if I was gonna mention something, but maybe I can keep it for later. But yeah, so it's mainly related to privacy, security, even national security, where like, imagine like some random groups are able to get more information about like creating some a harm weapon or something. So these things are things that we need to constrain and be careful when we are like using such a powerful technology. Okay. So a lot of things that are happening actually with neural networks and things that are evolving, things that like are GANs, generative adversarial networks, which is essentially just a way, it's actually the way that they were able to improve image generation, where they're essentially just trying to make a model that identifies a generated image, and then make the model that is generating the image improve upon that. So if there are two models, two neural networks, each of them, one of them they are essentially like playing against each other and competing. Which one is gonna be better, essentially? One that is trying to catch fake image generated images, and one that is trying to come up with the best fake image to even pass this judge. Another thing is like the neurosymbolic AI. The neurosymbolic AI is essentially a combination of two models, which is like neural coming from the neural network, which is just deep learning, but symbolic is just able to give some logic and reasoning behind that thing. So symbolic is like, for example, I don't know if you heard about like decision trees or random forest or things like that. Essentially, these are models that just logically split the data by yes or no questions. It just says yes or no questions until it reaches a specific output. So it's very reasonable, very logical way of classifying stuff. However, it doesn't give you as much like flexibility as the deep neural network, but it gives you a lot of explaining why was I able to reach this conclusion. One of the drawbacks that we'll talk about deep neural network is that it does not tell you how did I come up to this solution? How did I come up to this output? So this output is it's coming from a black box. Just I gave it a bunch of numbers and it returned a specific output. So you are just blindly, if the deep neural network tells you this guy has cancer, you are blindly just taking this output and saying, oh patient, oh, you have cancer. But we don't want that. We want to have some reasoning. Why does this patient has cancer? And then it will return, oh, this guy has like whatever like blood count and like whatever blood pressure and whatever. And therefore I was able to infer this kind of output. So the explainability in AI is one of the also like very like big fields in AI research, that they are trying to find ways of making each and every prediction or output from a model, they are able to get some information. Why did the model make this prediction? So a neurosymbolic AI is just a way of combining both deep neural network and reasoning in order to infer some output. Yeah, so there's a lot of like career opportunities right there in research. Like there's like tens of professors here at UCSD that do a lot of research. Some of them are like in trustworthy AI, like Lily Wang, or like privacy in like housing, or Juting in HDSI. So there's a lot of research that you can, if you're interested, you can join here. And yeah, like I was talking about, like the logical and reasoning deep learning. So this is where the most like important things lie. You're able to, right now we're able to get a lot of like the work done, but we're not able to say how were you able to get this prediction essentially. Yeah, so now that we have done the ethical consideration, and we can go ahead and do our simple demo. Anyone has any questions, concerns? Nothing? Cool. Okay. So this is a quick demo, which I can share after the lecture, of essentially we are gonna make a model, a neural network, that first we're gonna start simple, and we will just be able to predict what number is that. Is it from a 0 to 9? We're giving it value, we're giving it images, which is called an MNIST data. It's publicly available, anyone can get it. So once you get this data, I will show it to you right now, just give me a second. One of the things I hate about Colab is that it takes forever. So if you can not use Colab, do not use it. I do not like it. But the reason I'm using it because I can share it with everybody. And these like cute pets. So funny things, meanwhile, I can do some combos. But yeah, let me turn off the lights. Yeah, that's better, I think. So is it gonna run today, please? Yeah, I hate running live demos because it just, stuff. Is the internet on? Yes, it is. What's going on? Hopefully it works. So anyways, by the time it works. So essentially it's gonna be a model where like you have these images, 1, 2, 3, 4, 5, 6, whatever numbers it is, just handwritten numbers. And then it will just try to learn the patterns in these images. And once I give it new image, it's able to tell me whether this is like a 1 or a 2 or a 3 or a 4 or whatever. Okay, I don't know if it will run today, but anyways, so I thought of like leaving a bunch of stuff related, rectified linear unit. That's like what RELO stands for. Just like the max of whatever input you give between the input and the 0. There's another function that we use, which is softmax activation function. Softmax is just like a probability, just like converts whatever values you're giving into a probability, so that it's usually used in the last layer, where it's like the output layer. It just returns a bunch of probabilities from each perceptron, and it just classifies as the best class, essentially. Okay, I'm not sure if it will work, but anyways, here after running the model, you will get, I got by just 2 iterations, of learning. So it learned once, and then it learned another time. So it's like it did back propagation. And it got 98% accuracy. So it's pretty accurate, actually. Like it's able to now identified 98% of the numbers I draw correctly. And as you can see, this is an example. The predicted label was 9, and the drawn label was 9. So it's actually pretty good. Still not running. Okay. Also, this is code. You will be able to essentially, this cell, once you run it, you will get, what's going on? Yeah, this cell, once you run it, it will give you like a black canvas, and you can draw a number, and then it will give you the prediction. So it will give you the prediction every 2 seconds. You can adjust the time here, because I'm trying to give you time to change the number and then pass it to the model. Okay, anyways, I don't know what's going on. Yeah, there you go. Okay, the next model that I wanted to create was a model actually that predicts cats and dogs, since this was the example that I was giving at the beginning. And it was going to be also a deep neural network. However, it will involve a bunch of other layers. So you will see here like layers of like convolutions, max pool, and flatten, like some fancy words and things like that. However, I will just go over a little bit of like what convolution is, because at the beginning, for me personally, I thought it was like a fancy thing, and it's actually crazy, oh, convolution. However, convolution is actually just zooming into a specific like part of the image and taking it as a feature and giving it a score. So it's like you have the image here, and if you don't know that, images are just a bunch of numbers. So it's just a bunch of numbers. Each number represents a pixel. So it's like a grid of numbers. And then you have each of these squares is a pixel, and then each pixel has a value that represents the brightness. So all what convolution does, it just, you specify the size. So for example here, I say 3 by 3. That means it will just go into 3 by 3 pixels and then give it a score, and then move to the next 3 by 3, which is this one, and then give it a score, and so on. So it will just scan. Same thing as what we do as humans when you're trying to find any, read, for example, a name. You will start by scanning what is this letter, and then the next letter, and then you will combine all of this together. Same thing, it will just zoom into a specific part, and then give it a score, and then move on to the next. And what does this score represent? It represents the importance of this part, the importance of this subset of the image. Max pooling is just a way of combining all of these. But you don't have to, like, if you take like machine learning upper diff classes, you will be able to know more about it. However, it's like not that like crazy. It seems fancy, but it's not. And yeah, did it run, please? No? Okay, there's no hope. Okay, anyways, so because of the time, I just didn't run the model like for long. I just ran it for 5 iterations, and it was able to get like, the highest it was able to achieve was 67% accuracy. If I gave it like 20 more iterations or something, it would have probably reached like a 90% accuracy. And if you actually, I plotted a bunch of stuff here, which is like the validation and training lots. So like you have here, the first one is the accuracy. As you can see, it's just like each iteration, the trend is going upward. So just going upward. It was pretty bad, it was 54%. It went to like almost 66%. So it's like going upward, the trend is always going upward. For the loss, which is how we quantify how bad we're doing, we're actually going down. So we're actually doing, like, performing better. That means we're doing less worse than before, essentially. We're going down. So this represents information here. So I also plotted a bunch of like cats and dogs and our predicted value. So you can see here, this is the true value and this is our predicted value. And of course we don't need the true because we're humans. We're able to identify that by scanning the image. But yeah, you see like most of the times it's actually predicting correctly. But for this image, for example, it predicts dog by its cat. So probably just identified like some pattern in that image that said, oh, this looks more of a dog than a cat. But that's why we need to give it more examples or like give it more time to learn and identify more patterns to be able to get or achieve a higher accuracy. So any question about this? I'm sorry I wasn't able to run it live because Colab is just not the best thing ever to have, but any questions about this or about any of the models that is being used? And by the way, the packages, there's a lot of packages that you can use, and a lot of I would say frameworks. But I mean, there's PyTorch, TensorFlow, Keras. There's a bunch of Scalar. All of these have neural networks where you can use. There's I'm using also this image data generator. It's just a way of pipelining our images into the neural network. Yeah, I mean, I would probably share this notebook, and you guys can look through it on your own. And if you have any questions about it, feel free to ask. Okay, any questions? Is it cool? Okay. Cool. Let's what's going on, please? Yes. Okay, cool. Yeah.
Do you think the HTSI program set you up for success after graduating?
Well, okay, that's a hard question. However, it is the important one. I mean, I'm a little bit about me, guys. I'm an international student. I'm Egyptian, and I actually appreciate HDSI and how I learned a lot from it. However, there's a lot that could be also done better, and there's a lot of skills that we need to improve at, especially things that are more practical and or technical. There's a lot of tools that we are not being taught at school, and actually I don't know if I don't know of schools that actually teach these tools, but for some reason the work all companies expect you to know these tools. So definitely you have to work on your own personal projects and try to get gain as much as possible from these tools. But yeah, I mean, HDSI prepared me to go to Berkeley. That's what I would say. But yeah, so we have done the prediction model, which didn't work, but it happens. Yeah, we need a better IDE, internet IDE. Okay, so the last question that we want to answer is what do we have today that we did not have earlier, and why are we able to achieve so much super fast right now that we didn't have? Why didn't we just reach this 30, 40 years ago? Because neural networks, I think they have been around for decades, 30, 40 years. But why were we not able to create a ChatGPT 20 years ago? And it's actually resources. And resources, this encompasses a lot of information, a lot of things, from data, from compute power, from even thought process of how you can feature engineer these kind of information. So there's a lot of things that we have now, and largely it's the data that we have and the compute power. NVIDIA has been every year just producing some crazy chip that is able to process trillions of what is it called? I forgot, but operations, yeah. Trillions of operations right away in seconds. So it's crazy how our hardware is improving and how our data is also improving. Then the data is you have now the whole internet. You're able to get petabytes and more than, I don't know what is bigger than a petabyte, but a petabyte is essentially, I think is 1 million gigabyte, either 1 million or 1 billion gigabytes, something like that. So it's insane amount of data. So this amount of data, you are just giving it to the model, and the model is learning all of these random information. And we call this data big data. And why do we call it big data? The fancy word big? I mean, usually there's 3 words that involve this term, which is volume, velocity, and variety or variance. So essentially if you have a lot of gigabytes, and these gigabytes change frequently, and they are very different, like from texts to images to videos to whatever, then you can call whatever you have as big data. So volume, velocity, and variety. If you have these three, it's big data right away. And right now we have like a lot of it. So yeah, I mean, if you know, like ChatGPT took like 6 months of training. That means it has been like iterating and like making a bunch of like learning and like what is it called, iterations of learning for 6 months. 6 months of learning so that it's able to capture all of the internet. So ChatGPT was trained on the whole internet. So imagine like with the best hardware and the best resources, it took them 6 months. So, however, right now it's getting way better and way faster because 4 years ago we didn't have the Blackwell or like whatever chips that we have new right now. Yeah. So going back to facial recognition, one of the main things that everybody uses right now, probably. Like you just use your phone and you open it and it just sees your face and then, oh, there you go. So deep learning will capture every single part of your face and it will zoom into it and then it will check, oh, does this thing or like this part match whatever I have in memory of this person? And I mean, the convolutions that we're talking about, it'll just like zoom in, and then if you have like some kind of like a scar or something, it will be able to identify that, and it will be able to, if it didn't find it, maybe it will be it will have a high score of like saying, oh, maybe these two people are not the same, so I'm not gonna unlock the phone. So facial recognition is definitely one of the most important like things that we use every day, and everybody like use it seamlessly without actually knowing like how much like goes into like doing this thing and how fascinating like our computer is able to identify our faces. The next thing, natural language processing, which is like the main like the fastest growing thing right now, which is like ChatGPT. It's part of NLP. You are able to extract information by or like process information or do anything about information by natural language. Just typing a bunch of words and you're getting whatever you want, from code, from execution, from math, from research, from anything you're able to get by just natural language. And how does that work? NLP. If you want to learn about NLP, there's CEC 156, natural language processing. But yeah, NLP has a lot of things that goes to it. However, in DC80, I don't know if they removed the project or not. Hopefully they did not. You guys will be able, if you guys are data science majors, it's going to be, you're going to implement n-grams. Actually, in CC 150A as well. 150A will also implement n-grams, which is an algorithm that just by probability will predict the next word, essentially. So you have I, and then the most probably the next word after I is M, and then next, and then it will just predict by probability, will predict the next word or the next token. And actually, fun fact, I mean, I don't know if you know that, but like this is how ChatGPT works essentially. I mean, it has way more complex than that, but in simple high level like terms, it's actually just checking the probability. What is the most probable like output for this question? It's checking out when a person is asked this question, what is the highest, like what is the most probable answer to this question? So this is NLP. So going back to the advantages and disadvantages. So as we said, the advantages of neural network and deep learning is like we are able to achieve almost everything we have right now just by deep learning. You're able to recognize faces. You're able to speak to speak. You have AI assistants. You have healthcare diagnostics. You have you're able to create any agent for a specific thing that can tell you specifically about like agriculture, or another one, like my friend just created an agent that just like gets like law documents and is able to answer any law related questions that you have, and like things that related to specific like leases or like specific like acts or whatever. So there's a lot of potential that we're able to achieve by deep learning. However, like the drawbacks that we have, yes. What is it? I mean, we'll reach there sometime. I mean, they're working on. Elon Musk is working on it. I mean, there's this image. I think Elon Musk kissing one of his robots. So it's achieving love. Anyways, so the disadvantages. Of course, like the things that I said, that what didn't we have before? It's resources. It takes a lot of money. It takes millions and millions and billions of dollars to be able to create something like this. It's insane amount of money. It's insane amount like of water. It's insane amount like of things. Like water, for example, I just mentioned, you might be saying like, what does water have to do with that? Actually, ChatGPT, I think every like 4 questions or something, like people ask, it uses 1 liter of water. So each 4 questions, and see how many like billion. I don't know if that's like if that changed. I think that changed probably because I checked that like months ago. But it's insane that we have 8 billion people in the world. Probably 1 billion of these like uses AI, and they are just like by 4 questions, they're using 1 liter of water. See how many millions of liters of water you can use. And why do we use water? It's to cool down just the processors that we are computing like this information with. So definitely money is a big thing. Hardware, there's a lot of limitation with hardware, but you can say, oh, just get like 1 million processors or whatever. It's not very cost efficient. But yeah, I mean, theoretically it could work. Yeah, there's a lot of risks related to bias. And what does bias have to do with this? It's because bias is always in our data. The data always has some kind of bias. So this bias can lead to a lot of like bad like predictions. For instance, Gemini was actually at the beginning of its launch, it was actually racist for some kind of racist. But it's essentially just like whenever you ask it to generate an image of an Australian person, it will generate an image of a black person with like some facial characteristics of Australian. So it's just like saying Australian people are black. But it's just whenever you ask about any person, it will just generate a black person. But why is that? It's just because our data, it was just related, Google was trying to fine-tune the data to not be racist against black people, but now it became racist against white people or like different people. So it's like, it gets a lot of like, there's a lot of like biases that happen within the data and how we use our data that we need to take care of all of these aspects. So it's a lot to take care of. That's why there's just a specific sector called responsible AI. And if you want to take the class, there's called a class 261, DC 261, it's called responsible AI, the data science, which just like teaches you about like causal inference and like a bunch of things related to like fairness and like, things related to biases. And yeah, the last thing is hallucination. Hallucination is a big thing. For some reason, people are not talking about it anymore. However, it's still there, and it will always be there because we're talking about probability. And hallucination is just when the probability just did not work, and like you now got a wrong result because the highest probability was a wrong result. Just like some random information just pop up. So this hallucination can lead to like, if you are just depending on AI without a human intervention and like checking on the work of the AI, then you're actually like prone to a lot of like problems essentially. But yeah, so given that it needs that much like resources, I mean, are we able to find a way where we can just not reinvent the wheel again and not have to pay a lot of money to improve our things or like to train our model? So there are actually a bunch of things, like, for example, how is ChatGPT able to release a model every couple of months, or Anthropic just released Claude 4, or like, how are these able to do that? They're just using ways of learning where like they are just increasing on the data for the model and fine-tuning it without having to restart all over again. And one of the ways is called transfer learning. And transfer learning is essentially just using a pre-trained model, and it will essentially have the first initial steps of extracting the features so that it essentially you don't have to do all over the steps again. So for example, it will learn how to get the like in a face, for example, you will have a model, like for example, a resident model, which is a model I used for my capstone to predict the sepsis. To predict actually pneumonia from chest x-rays. So it will just use whatever information it has on how to get the features and the convolutions, extract this information, and now it has the weights already set, and I will not have to retrain like 50 layers of weights. I will just focus on a couple of layers where it will just like be customized into my specific data. So let's say I have 50, the ResNet 50 is like a 50-layer deep neural network. And then these 50 are already trained. It has the weights. They're trained on a generalized data. And now that we want to give it, make prediction on chest x-rays, we just unfroze or like made it like learn on the last 2 layers. So the last 2 layers will be able to change the weights, and the first 48 layers, they will not be affected at all. So I'm just like, instead of training 50 layers, I'm just training 2 layers, which saves a lot of money and a lot of compute power. Even like these 2 layers, it took us, I think it was like 30 minutes to train, like every time. So in order to fine tune, it took us days. But I mean, just each time it takes 30 minutes, and it's only 2 layers, nothing much. And we were not even training on that much data. It was like, I think it was like 3,000 images or something like that. But yeah, so transfer learning is definitely a big thing right now. There's a lot of other ways of learning that you can reuse essentially. Like, for example, what is it called? Reinforcement learning, which you're going to talk about. Reinforcement learning is just a way of like feedback loop, having a feedback where like you're able to make your model learn with further like information essentially. Yeah, so that was the main things that we have here. So I will open it for questions and discussions. Anyone have any questions? Concerns? Nothing? Yes? Sorry? You want to learn about it or do a project? To learn, if you want to learn about it, I will definitely encourage you. Like, there's a very good course at MIT that is available online, and there's the Stanford course that is also available online. Like, these two are like one of the best ways of learning. Like anything related to AI, they're really good at it, and like there's a lot of sponsors that like make them do this. Like it's like Google and like a lot and OpenAI, like all of them get involved in these courses so that they are able to like reach the most like diverse people essentially. So definitely Stanford and MIT, they have public early resources. Yes.
You mentioned earlier that a lot of the best tools like aren't taught to us here. What are like the top 3 tools you recommend we learn on our own time?
Okay, things that we are not taught. Okay, on top of my head, I mean, for data science specifically, we're technically not taught GitHub, which is something we use, but we do not learn it. And there's a lot that goes into it, not only just git add, git push that goes to it. There's a lot of git commit, git push. There's a lot that goes there. So definitely GitHub. And so it will be also like kind of a hot take right now, but like data structures right now is actually not the best being taught. I've taught data structures for like a year, or like I tutored for a year, and it's getting worse. So you need to learn data structures on your own, and like probably do a lot of lead code so that you learn actually data structures I mean, lead code, I personally, I'm not a fan of lead code because it's just like stupid questions. However, I can't deny that it's actually useful, that it makes you like think of how to use whatever tools you have to solve even a stupid question. And then a third one would be, let me think, the most important tool. I mean, to be fair, there will be like specific stuff related to, like, for example, Docker, for example, or like things related to the cloud. These things are like in a lot of data science and software engineering positions. These things are always there in the job description, but they are never, Docker specifically, which is one of the essential parts, nobody teaches you Docker here. So Docker is also a very important thing that you can learn. There's a bunch of other things I don't want to mention because it's like specific tools for specific jobs. But if you want to know what tools you need to learn, you should probably like go to a careers page for the company that you want to work for, say Apple, open, check their internship or like their full-time position. What is like the tools that they're using, and then you're able to like, oh, okay, they want that thing, I'm gonna learn it in this amount of weeks, and so on. It's actually the advice that I got from Kyle when I asked the same question like a year ago. So, yeah. Any other questions, concerns, thoughts? Anyone here does not use ChatGPT or LLMs? Other than the person in the back. You don't use it at all? Okay, that's cool. I mean, I personally, I did not use it at the beginning, and I was so happy that I'm so happy that I did not use it, because now at least I have some basic, very low level, foundation, very tiny bit. However, it's actually useful right now, because after using it, my intellect is just going down. So I personally, although it's fascinating and I always use it, I still do not advise people to use it that much or rely on it, because it's not good. it's getting us really in a bad spot. Yeah, okay. I think that's it. So thank you guys. And if you guys have any questions, just let me know. Thank you.